Okay. What I want to talk about now is a application of regression type techniques for solving classification problems. So quite often we are given classification problems. In a classification problem, you've got input examples that are labeled as belonging to some kind of a class. Perhaps we would like to predict somebody's gender given some statistics about them. We would like to predict their party affiliation. We would like to predict, given a tissue sample, is it cancerous or benign? Okay, you know, an email, is it spam or is it a real piece of email? So classification problem is a problem that assigns a label to an input record. Any questions about that? And, you know, so this is obviously an important class of problems. One way that you might think about doing it, which actually I will argue, might be that we could use linear regression to solve classification problems. Have we talked in here about any method for solving classification problems? We certainly talked about classification problem. Let's go back here. Is there any method that we have talked about how you would solve a classification problem? Okay, I don't think we may not even have discussed any methods yet so far, right? Does anybody have a group project, a semester project where they're doing some classification? Okay, this is a little. Okay, that's a little bit of a surprise, but again, it should be clear it's an important thing. It should be clear it comes up a lot. It's a surprise that it may have worked out where I don't see any of the projects, at least in the room now, that have been classified with that. But how might we solve a classification problem? And one way to do it would be the following. Okay, we could assign each class take the two classes. Typically, let's think about binary classification problems first, where there's two classes. Okay, and we assign one class the number of 0, and the other one the class 1. And by convention, we say that the positive class, which is the thing that we're more interested in, kind of gets 1. The negative class is class 0. And if we think about that, now if the class is given, if the class that the people have, or the objects have, is given by a number, we can now think about using linear regression with this as the target. Does everybody kind of get that idea? Okay? If you want to build something to predict the class number, okay, if the class number is a number, linear regression is something that takes the features and munches on them and produces a number. And we train it so that it tries to predict that number as well as possible. That would be an argument that we could use linear regression for building classifiers. Does everybody kind of get that idea? Any questions about that? Now this turns out to be a not very good idea. Okay, let's make sure we understand what the idea is and understand why this is not a good idea. Okay, so what are we having? Let's say that this is a one variable classification project. Let's say that you want to identify whether or not you've got, let's say our classes there's two types of integers in the world, numbers in the world. There are positive numbers and negative numbers. The positive numbers are members of the positive class, and negative numbers are members of the negative class. Does everybody see that? And here we've got, so here is our value x. The positive class has value 1. So these are points going to be a positive number with the y coordinate being 1. This is the negative class. The negative class we said was assigned the label of 0, right? So does everybody see that we could have a classification problem where we would want to try to separate, let's say, if we're given examples of positive numbers and negative numbers, we would like to try to figure out, how can I tell what is a positive number or a negative number, right? Now, if we fit this in a regression line, okay, that in this case, I guess it sort of does an okay job. Okay, here we have some examples here. Here Here we have a regression, all the positive examples, negative examples. Red is what I show as the regression line. And in general, I guess for this particular example, if it really was positive and negative numbers, I guess because this regression line seems to go through the value 0.5, right? That everything that was, in this case, labeled as positive would correspond to a score above y.5, meaning it's more like, so an item like this, how would we interpret for the value of 2? We would interpret this perhaps as being what is the probability or likelihood or confidence that we're declaring it to be a positive number. Does everybody see that idea? So kind of the midpoint here, if this is the positive class is y1, if the negative class is y0, you could imagine having a regression line that for any value is going to return a number. If you have a threshold built in, and a logical threshold is perhaps the middle between the two classes, right? You could say that if you're above 0.5, we will say you're a positive class member. If you're below 0.5, you're a negative class member. Does everybody kind of see that? So we could make that work. But is this red line the line that really discriminates between positive and negative numbers? Okay. Yeah?
So no, I don't think this line, I'm not really getting what this line is trying to do.
What is the red line doing?
Yeah.
Okay, let's make sure we understand what it is. Suppose, let's say, I am trying to figure out, I have a training set that said, minus 2 belongs to a class called n, and minus 7 belongs to a class called n, and 3 belongs to a class called p, and 5 belongs to a class called p. And I am now trying to, for a new number, I have a new number coming along, 4. I want to try to predict, is it p or n, right? Now, how might I do this using my tools from regression? One idea is to say, let's call the negative class 0. Let's call the positive class 1.
So when you say regression, you mean linear regression?
Linear regression, okay? Linear regression, the thing we've been talking about, right? Now I've got points where this is x and this is y, right? I could now try to fit a line given x that best approximates y, right? That's what linear regression is, least squares type of thing, right? That is this red line here, okay? And if we think about it, if the y value is supposed to encode the class number, this is not a completely stupid thing to do, right? Does everybody see on this example, if I give you a number, again, for this particular red line, if I give you a positive number, okay, it will, give me a number, a y value that's larger than a half. Does everybody see that? Okay, and that might mean we say, well, that means it's more close to the first class than to the second class, to class 1 than class 0. Does everybody see that? So you might think about this as being a way of predicting the classes. Does everybody see that? Okay. Now, is this a good way or a bad way to do it? What potential problem? Does everybody understand the scheme? Okay, before we, to think about it. Okay. Now, what might make this a bad scheme? Okay. Well, you say when they can't be linearly separated. Well, first of all, notice that this regression line has nothing to do with linearly separated. The right way to separate positive from negative numbers is the green line, right? If you are x is greater than 0, you're positive, and if y is less than 0, you're negative. Does everybody agree with that? So the right thing that you want is a separator, okay? This class predictor thing is not a separator. Does everybody kind of think about it? If we predict our regression line is trying to predict the class number, right? That is different than looking for a separator. Does everybody agree with that, right? Now, what else would be a weird thing about using regression for this? If we take a look at this example, what's going to happen to the regression line if I add another point over here? This is minus, what's the right scale here? It's minus 115, right? What is going to happen to the regression line here? This is the point minus 115, 0. Okay? What is going to happen to that red regression line, yeah?
The line will shift and the line will shift more towards the negative numbers, and then it will predict a positive value for the negative numbers.
Does everybody see that if I do that thing, this red line is going to shift up to the point that suddenly this magic 1/2 thing isn't going to cut it, right? All of these negative examples here will suddenly now get scored as positive because the regression line is going to be working so hard to satisfy that outlier. Any questions about that? Okay. The threshold separator, the green separator, is every bit as valid as it was before, right? But the regression line predicting the classes is now bad. Does everybody get that idea? Okay. So this idea of using linear regression to predict the class number, maybe we could do it, but there seem to be problems with that. Any questions?
If we set a threshold at 0, suppose.
A threshold of 0. What do you mean by a threshold of 0?
The line dividing that, like in half, like you take a 0.5 over here, right?
Yeah.
You take it 0, suppose. In that case, will it correctly classify? Or
You're saying that if I set the threshold as being, so long as it's above 0, call it negative, I don't see where you would, I could put points in weird places such that any threshold, I think, is going to be wrong, right? Does everybody kind of see that? This is a weird case because a training example that should be easily handled is what's messing us up. That's kind of the interesting question here, right? The minus 115 is easy to tell that it's negative, right? It's more negative than anything we have seen before. And yet that training example is what's messing us up, okay? So that's bad karma about the linear regression method here. Any questions? Okay. So that is going to introduce us to the idea that what we really kind of want is not to think about and again, there's other weirdnesses about predicting the class number. This is really right. Y here is supposed to be the class number. Notice that normally for 137, by this regression line, what class is item, minus 115 going to be? If this is the line y equals x, that's going to be y equals minus 1, which seems weird. That's not close to the class value of 0, right? So, so it seems weird to try to predict the class number, okay? Instead, the right, let's say, mechanism to think when we're thinking about classification is not trying to predict the class, particularly regression style, but that we are looking for separating lines. We have examples of one class, we have example in feature space, we have examples of in another thing, and we want to try to draw a boundary such that the points in one side of the boundary are in one class and the points in the other side are the other class. Any questions? So our goal is to try to find separating lines now, okay, and not class predictions. Any questions? Okay. Now, we notice that sometimes our separating bounds, okay, are not going to be lines in a particular case, right? Let's say we have examples of people who are near the center of the circle and people who are near the origin. Let's say that all the members of class 1 are near the origin and all the members of class 2 are in outer space, they're further away, right? Does everybody see here that the separating thing that we want is actually, in this case, a circle. Okay? Any questions about that? So we're going to talk about separating lines. Recognize that we might want nonlinear boundaries, but recognize that we aren't really going to be so, that if we have a feature matrix seeded with nonlinear features, a linear classifier would deal with that. Suppose we have a world here where we've got an x1 and an x2, and let's say that all the bad guys, or all the round elements, are in a circle of radius 1. Is there a linear classifier that separates them? You say no. But what if our feature matrix was x1 and x2, if these were the two variables, then there was no linear way to separate them. But what would be a linear way of doing it? If I'm remembering my circle business right, if I had x1, if this is the x1 axis, and this is the x2 axis, right? Suppose I have x1 and x squared and x2 squared also added as features in my matrix. Does everybody see that? Now could I build a linear separator? Okay, if this was variable v1, v2, v3, v4, then the answer is if v1 plus v2 is less than 1, then that would be, if v3 plus v4 is less than 1, does everybody agree that this is now a linear separator, something that could find linear separators in this matrix, would certainly be able to find it, but we get the effect of a nonlinear boundary. Does everybody see this? This is the same trick that we use with linear regression to give it the power to do nonlinear functions. Any questions about that? Okay. Any questions? Okay. So the world here is going to be a lot like linear regression. If we're going to try to look for linear functions, if in fact we seed it with nonlinear features, we will get nonlinear separators. Okay. And that's a good thing. Any questions? Okay, good. But on the other hand, we have to make sure we give it kind of the right regression problem. Okay, and it should be clear that predicting class boundaries, class numbers was not it. Instead, what we're going to do is use a friend that we have discussed a couple of times in here called the Logit function. Again, we're going to be looking for something called logistic regression. Where does the logist come from the logistic regression? It's coming from the Logit function. The Logit function, if we remember, was a function that had the property that for 0, the value was 1/2. As x got very, very negative, the value of it went to 0. Actually, I forgot this. Somebody send me mail. This is supposed to be a 0 here. Okay? Okay? When we got very, very positive, the value went to 1. Okay? Does everybody kind of remember that? Again, remember there's a 0 for where the -1 is, so that I feel a little bad about. But if we take a look at it, if x is equal to 0, e to the -0 is what? Okay? Anything to the 0 is 1. 1 plus 1 is 2. 1 over 2 is 1/2, right? If x is very negative, if x is very, very negative, something negative times something negative is very positive, right? E to the something positive, very positive, is huge. 1 over something huge is going to be 0. Does everybody agree with that? And suppose, let's say that x is negative, that x is positive, very, very positive. E to the minus something positive is 1 over infinity. 1 over infinity is 0. 1 over 1 plus 0 is 0, right? So this function has the properties that we want that on one end it gets more and more close to 0, on one end it gets more and more close to 1, and it passes through a half as we go through it. Okay, any questions? So the property that is good here is that if we take x as a variable of in-classness, let's say x was a variable that got higher the more likely it was for an element to be positive. If we interpret the value from the Logit function as the probability of it being positive, for a very positive thing, we're going to get the probability will get close to 1. For a negative element, the probability of it being in that class will be close to 0, right? So the claim would be that a Logit function that is interpreting the result as what's the probability of being in a class gives us something that we kind of like. It has the properties that we would like to do. It's going to return, for any value x, it's going to return the probability of it being in that class. Any questions about that? Okay.
Why is it the probability of it being in the class? Isn't it just a number that we...
It's a number between 0 and 1.
Right.
Now, a number between 0 and 1, we can, without a guilty conscience, interpret as a probability.
Right, but we have to, map it. That number is just dimensionless, or, not dimensionless, but, it doesn't have any inherent probability-ness, right? We have to, map a value of, if we return a value of 0.9 in a Logit function, that doesn't mean it's 90. We have to, map it to some likelihood.
So what we're going to do is we would like this function should have an interpretation. Suppose this interpretation was, what's the probability of it being a member of the positive class? Okay? Now let's think about it from our positive. Let's think what would happen on our positive-negative number example, right? What's the probability that 10 is going to be a positive number? Very high. What's the probability that 0.1 is a positive number? Well, it's less than 1, but it's more than a half, right? What was the probability that minus 115 was a negative number? That's going to be very close to 0, right? So in principle, if we're going to use this as a separating boundary, what we would like to think is that the easy cases, the ones that are far from, let's say, the boundary, we give a very confidence view on. Whereas something very, very close to the boundary, we give a much more equivocal call, right? Does everybody kind of see that? And that if we were empirically trying to learn what's a positive and negative number, unless we really have training incidents that show us that 0.00000001 is positive, we might be a little more less confident about our judgment, right? And that means a probability is doing kind of the right thing. Any questions?
Sir, if we integrate the functions between minus infinity to plus infinity, will it give 1?
What?
If we integrate the function between minus infinity to plus infinity, will it give 1? Like the area under the curve.
Okay, so what you're trying to say here is the area under this curve going to be equal to 1? That's an interesting question. First of all, let's think about this. The answer I am going to claim is no, because, and the proof of it is very simple, that as we move further and further out, does everybody agree that if this is 1, as we make x very, 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 very big, we're still multiplying that by 1. As x goes to infinity, the area under this curve is going to be infinite, right? But that's not really what we're actually asking. It doesn't need to be a probability distribution as such. This is a function that, given an example, returns what is the probability of it being in the class. And the probability, what we care about is that the probability of it being in the class plus the probability of it not being in the class is 1. Does everybody agree with that? And here, the fact that it is symmetric, okay, is what really is kind of gives you that, right? So anyway, so what we need is that the probability of it being in the class plus the probability of it not being in the class is 1, right? And if it's a two-class problem, like here's the proof. If it's a two-class problem and the probability of it being in the class is x, what's the probability of it not being in the class? Has to be 1 minus x, right? Yeah.
So aren't we going to have another function, though, that returns the value that we feed to this function?
Ah, you're saying that somehow, well, you're saying there's a couple things that are bothering you.
Yeah.
One thing that is bothering you, although you didn't say it, is that this thing only has one argument.
Yeah.
And look at this. Here we had 4 variables. We somehow have to get these variables into that one argument, right? So what's really the truth is this is not what we're really learning. This Logit function is the behavior that we would like our predictive system to have. What we really want to learn, to be precise, is what is a function h such that if I give you an input vector, okay, you could feed into feed h of x into this in as the argument here and have it make the classification on that linear function h. Okay? Does everybody kind of see that? Okay? So the input, what we're really going to want to do, the place where the regression is going to come in, is we want to take a bunch of, a bunch of points and fit these parameters w to compute so that we have a linear function of the variables, such that when we feed the result of that to our Logit function, okay, it's going to always return a value of 0 or between 0 and 1. For the positive examples, the number is typically as close to 1 as it can be, and for the negative examples, the value is as close to 0 as it could be. That's what we want to do here. Any questions about that? Yes?
But so this value, the function h is still, it's an output variable, right? I mean, it's...
H is an output variable. It's a score. If you think about it, it's sort of like a score. It's taking the, these input variables and weighing them, a linear combination of them, a linear function of them, weighing them to get a score. And the Logit function is going to use that score to make a decision what is the probability of it being positive.
So all of these scores, it's still a vector, right? Because they all represent certain points in space.
Okay, so no, this is for, once we have the coefficients, this is h is a function that takes any one point and converts it to a score. Does everybody see it? Before we were fitting the score might have been the class number. That was what we were, that was what you were doing with the earliest formulation of this thing. Here what we're instead going to do is we're going to use this to compute a score, and we're going to take that score and plug that into as the argument to our Logit function. Okay? And now, for any input vector x, it's going to determine a probability. What is the probability that it is a member of this class? Okay? Any questions about that?
Will we use linear regression for calculating h?
So how are we? The next question is going to be how do we compute how do we figure out what the parameters of h are, meaning those w's, right? Okay? But first, let's just make sure we understand the formulation here and why this is kind of a good formulation. Yeah.
So the behavior of the underlying Logit function will remain the same, right? Like for high values of x, it is going to go near 1, and for like low values of x, it's going to go near
Right. So what's interesting here is that if our value h does a good job of classifying it, it's going to be the case that the Logit function is going to return a value of near 0 for all negative values. It's going to return a value of near 1 for positive examples, right? That's what we would like it to do.
So if it is a good function, we will be ideally getting values close to 0 and 1 for the values that we plug into this formula.
In an ideal world, if we had a really great classifier, well, our dream would be that when we plug in our values of x, out of f of x, we're going to get a values that are either going to be close to 0 or close to 1. Okay, that means that we're making very confident decisions. Hopefully we are making confident decisions, and hopefully our decisions are also right. Okay, those are the two things that you would like it to be. Any questions about that? Yeah. M is the number of parameters. So here M would be 4. 1, 2, 3, 4. Here in this notation, which may not be the notation that I have used so far. Yeah, so far what we use, we assume we had n examples and m parameters. I think this is the same notation that I used throughout the book, right? We have n training instances, each of which is an m-dimensional thing. Okay? Yeah.
For example, how do I determine the threshold of how, I mean, is it a self-determined threshold?
So how do I determine the threshold of it? Now, by this you mean how do I determine, I get a score back from this logistic classifier, okay? How do I interpret it? Well, because that is getting pumped through this function, right? It is going to interpret things where if h is positive, it is going to be returning a value that is greater than 1/2. And if h is negative, it's going to return a value less than 1/2. Okay?
Irrespective of the scenario I'm dealing with, 0.5 is the threshold that separates one class from the other.
0.5 is what, if we have a two-class problem, if we're interpreting something as what's the probability of being in one class or the other, 0.5 is the bounds of no knowledge, right? If I want a classifier for my next coin flip, is it going to come up heads or tails? Okay, I will predict heads with a probability of 0.5. I have a 0.5 chance of calling the next flip a head, right? Any questions about that?
We can't use it for more than two classes, right?
Right now, let's just think about it for two classes. We'll talk a little bit about multiple classes later and how we will deal with it. But two classes covers a lot of different things. So two classes is still a very interesting problem, right? One class would not be interesting, right? But two classes is interesting. Any questions? And notice that you may say, well, wait a second, what about the threshold? How do I know that when the score is good or bad? Notice that if the thing is trained properly, W1 is, in some sense, W0 is sort of like a threshold, right? If you look at this thing, this is the sum, the weighted sum of the x values, right? This here is, we think of it as the intercept. But another way that we think about it, it's how much where do we put the scale such that this thing has to be that much bigger than this value for it to be positive, right? So in principle, if we're learning this with the idea of accurately classifying the points, h sub x should have the property that positive values will be, positive in training class cases will be positive numbers for h of x. Okay? Any questions about it? And so we get the threshold parameter kind of can drop out naturally from this. Any questions? Yes or no? Okay, good. Now, how can we train this thing? So does everybody kind of agree that what we would like to do, we are given as input a bunch of examples, okay? We're given examples of whether their class is the negative class or the positive class. And we would like to now try to compute what those W1 is, such that we identify what would be the best possible separator. Okay? Any questions? Okay. So again, our training examples are labeled as being class 1 or class 2. We seek to identify the coefficient such that on all the positive examples, we get high probabilities. And on the negative examples, we tend to get low probabilities. And to determine how good a set of coefficients are, is we need a cost function to decide how many points do we give you for giving a 0.75 call to this. There's a positive object. let's think a little bit about how we would want to score these things. Suppose I am trying to predict the probability, I have a positive class member. And suppose my scoring function says the probability of it being a positive item was 0.99. Do we think that's good or performance or bad performance? Okay. If we look at an item and we say there's a 0.99 chance of probability of it being positive, and it is positive, we want to say that's good, right? What if we said it was a 0.75 chance of being positive? Do we want to say that that's good? It's less good. It should be clear that that's less good, right? What if we said there was a 0.01 probability of it being positive? We would like to say that that is bad. Does everybody see this? Now we need to have a concrete instantation of what it means to be good and bad. We have a qualitative sense of thought. We need to come up with a scoring function. So what we would like is a function that does something like this, okay? And I think if we look at the curves, this is going to be obvious. Let's say, what is the penalty? Let's say that our h function returns a probability governed by this red curve, where x is the probability that returned for it. Let's let y be our happiness level, or the cost, or the penalty we want to give to that answer. Okay? It should be clear that if we have a positive example, and our probability was very, very close to 1, our penalty should be very, very small. We are happy with what we have achieved, right? As we move further and further away, we are less and less happy. Does everybody see that?
Yeah, but
why do we choose this curve? Well, there's going to be two reasons as far as I'm going to tell that we're going to choose this curve. One is, I think that we do want ourselves to be at least, have our unhappiness growing monotonically. And I think that we want to be really upset if we say something is almost certainly positive and it is negative, right? So why are people angry at pollsters today? We are right after the election. Why are we angry at the pollsters? If the pollsters had said, oh, it's 50-50 and I don't know what's happening, and then they said Trump won, no one would want to shoot the pollster, right? But the pollsters said, you were the one that sent me mail saying, there were these pollsters from Princeton, you were sending me mail saying, it's so obviously 99% true that Clinton's going to win, and the other the state silver doesn't see that, okay? Okay, you want to shoot that pollster, don't you? And that's exactly kind of what we're doing here. You don't want to say, well, that's twice as bad as if he had said it was a coin toss. You want to punish him, right? And that's really what this curve is saying. So this is a curve that is really going to punish you for very wrong predictions. It's going to be less punishing on you being indecisive, right? That's kind of what this is saying here. We can argue perhaps whether that's the right measure, but that's what this is doing. And so why are we going to be doing it? Because I think that's a defensible thing to want to do, and because there are nice functions that generate these curves that will end up yielding a convex optimization problem, and then we can apply our gradient descent search to finding the right parameters. That's why this is going to be the right parameters, okay? Or a perfectly good set of parameters, right? Any questions? So we want it to be the case that if the thing is positive, we want to give you little error for being giving a high number, a lot of error for giving a very, very close to 0 number, right? Likewise, if it's a member of the negative class, we want to give you very little error for saying 0 or near 0, and a lot of error for saying the probability of being positive is close to 1. Any questions? So it turns out what functions give the shape of this that we would like, that we're seeing here, okay? It turns out that they are it is the minus log function. And let's go through and think about this a little bit. What do we know about probabilities? Probabilities have the property that they are between 0 and 1. Okay? what is the log of 1? Okay, again, I have a hard time thinking these through, but I know that x to the log, b to the log base b of x is going to be x. Does everybody see that? So if I want x to be 0, what is it that the log base b is going to have to be? What do I have to raise b to get 0, assuming b is something like 2 or some positive number? Okay. What is it? Wait, hold on, wait. Did I get this backwards? The log of 1, not 0. If I had 1 here, excuse me. That's what I'm looking for, right? What is the thing that we have to raise b to get to the 1? B to the 0 for any value of b that is interesting is 1, right? So that's an argument that if we want the log of 1 would be 0, okay? What is the log of 0? Let's think a little bit about this. This is one I have a harder time. What is the log of 0? Okay? Suppose that this thing is equal to 0. Well, how do we get b to something to be equal to 0? Okay? We have to raise it to a negative number. Does everybody see that? Because assuming b is a positive, let's say b is 2 or 10 or something like that. If we raise something to a negative power, that's going to be 1 over b to the x. Does everybody see that? And now the higher I can make it, okay, the closer to 0 I will approach. Does everybody see that? So the claim is that log of 0 is minus infinity. Does everybody kind of get that idea? Okay. And if we believe that, if we can say that the cost for a positive example should be minus the log of this. Why is it? Let's think about the positive examples. For 1 minus 0 is 0, right? For an infinite, okay, let me just take a look at this thing. Let's go back to this because I get this a little bit confused, but let's just double check it. We agree that the log of 0 is minus infinity. The log of 1 is 0, right? If I take minus log as my error function for a positive example, minus the log of this, when it's near 1 is going to be almost 0. When we get 0, we're near 0, minus the log of something near 0 is going to be a very large value. Does everybody agree with that? That I now believe. So the claim is that minus log of whatever the class probability is a good punishment for the case of positive examples. It's clear that what we want for the negative examples is a reflection of this. Does everybody see it? That we kind of want to, equally far this way is what we want it to be that way, right? And if you work that out, 1 minus the class probability, the log of 1 minus the class probability gives us this blue function, okay? And so this is the error function that we want for positive examples. This is the error function we want for the negative examples. Any questions? And if we believe that, then the claim would be, what should our training criteria that we want to minimize? It wants to be that we want to sum up over all of our training instances. Okay, all n of them. Actually, there should be an n here. I messed this up. There should be an n. Okay, all training instances. We want to come up with what is the cost of our prediction, okay, given the real class label, right? And This is the punishment we want to pay for a positive instance. This is the punishment we want to pay for a negative instance, right? The kind of cool thing is, if we multiply the positive instance, the punishment for a positive thing, by the class variable yi, the class variable is either going to be 0 or 1. Does everybody agree here that here we've got the training examples are either labeled as 0 or 1? If I multiply something by 0 or 1, that's intended to punish things for positive instances. If it was a positive instance, it would be 1 times the punishment. So it faces the punishment. If it was a 0, it's not getting any punishment. Does everybody see that? So a negative instance is not going to be punished by this criteria if we have the class variable times the intended punishment. How many people are with me here? Okay, any questions? Likewise, if we multiply the one that's intended for negative things by 1 minus the class variable, if the class variable was positive, 1 minus positive 1 is 0, this punishment would not apply to something that was labeled as a positive instance, right? But if it was a negative instance, 1 minus 0 is 1, it will pay that. So what's kind of neat about this criteria, this is summing up the punishment we are facing for each training example, right? Does everybody kind of get that idea?
Why we are adding negative sign?
Why is the negative sign? Because I think the negative sign is because all of these punishments, remember, if you looked at the original here, let's look at this thing. We said that the cost function should be negative, right, for both this and this. Because the log of a value that's less than 1 is going to be negative, right? So this is saying that the error cost, okay, since this is a negative number and this is a negative number, by multiplying the outside by a negative number, we're making it positive, right? So what do we want to do? We want to find what are the parameters w that will minimize this function. Does everybody see that? Okay. And what is f of w? Well, f of w, this f thing, is going to be the Logit function applied to the linear combination of the x values and w, right? Any questions about that? If you see that, oh yeah, question. Yes, but okay, so we want to now calculate these coefficients the same way we calculated them in linear regression. How did we calculate them in linear regression? Well, when we were doing it by gradient descent search, what did we do? We had an error function. Remember, we considered the coefficients as a point in space, right? And we defined an error function for the set of coefficients, which was the sum of squared error for that value of the coefficients, right? And we saw the magical property that, in fact, this happened to be, that's supposed to be a bowl, okay, you can't see it, but what was the important point? The important point was that this was the error dimension, okay? Every point here was representing a value of the coefficients. For those coefficients, there was an error represented by a point on the surface. To find the coefficients that minimized error, because this function was convex, we could just keep walking downward until there was no place to go, right? And the amazing thing is this kind of funny looking function also has the property that it is convex. This is the error of how unhappy or unhappy we should be with a particular set of coefficients. Okay? And the amazing thing is that the unhappiness function turns out to be a convex thing. And because it's a convex thing, we can use gradient descent search and find the right parameters. Any questions about that? So this is how logistic regression works. And now I claim we have done it. We can now use this technique to find the best possible linear separator, okay, between any representatives of any two classes in any number of dimensions, okay, using the same technology. Any questions about it?
Can you just give a summary, like how we do it?
How do we do it? The world should look exactly the same as it did in linear regression by gradient descent search, the way it looked on Monday. Remember, back to Monday. It was a happier time in many ways, okay? But what was the thing that we knew? We had as input. There was a space of, there was some X space of, there was a parameter space, W1, W2, however many parameters we wanted in our model. We had an error function that basically took for any point in parameter space, would use those as coefficients. We could figure out what was, for that parameter, those parameters, what was the prediction it would give on one of our training examples. We could subtract that from the actual answer and square it, and sum this up over on. That was our error function, right? And because that error function had the property that it was convex, we could start from a random point set of parameters, okay, and then find a direction that would lead us down, right? Because it was convex, there is one set of parameters that is best, okay, that will minimize the error function. We could always find which direction will walk us towards it. And we kept walking towards it until we found it, right? And that's the same thing we're going to do now. We want to find what is the right parameter, coefficient parameter W, vector W, right? This is the cost of how unhappy are we with a given separator. Remember, F here is encoding this logistic function where the argument is that that linear function, W dot x, right? This was the error function, the undesirability, the thing that would measure the undesirability of a particular value of W. Okay? Particular vector W. And therefore, because this error function is convex, we can use the same bop thing down, gradient descent search, to find the minimum. And therefore, we can find the best parameters to separate this. Any questions?
So the only difference between linear regression and logistic regression is in the cost function?
I guess that's, yeah, the only difference between linear regression and logistic regression is really the cost function. It needs to be different because it's a different kind of a problem, right? This is a classification, that was a regression thing. But basically, that's what the story is, right? We have a different cost function, but we want to find the parameters that optimize the cost function. And that's why both of them are solved by gradient descent search. Any questions? Yes? Well, suppose that the points are mixed. This is not saying that the parameters W are going to perfectly separate the positive examples from the negative examples. It says that the parameters W are going to make this function as happy as it can be. Does everybody see that? So, what am I going to do? Suppose we have an example here where, let's say, I declare that this is a positive number, this is a positive number, and this is a positive number, and this is a negative number. Okay? Well, what would this mean? Okay? Is there a threshold to separate the positive numbers from the negative numbers as good as possible? No. Well, there's no threshold that will perfectly separate them, right? But what is the threshold that I'd probably be happiest with? Maybe I would want it over here. Maybe I would want it over here. Which one would I want it be? Whatever minimizes this, right? This is a criteria, and this would now find a particular one. It won't find a perfect separator because you can't find it, but it will find some kind of separating function. Any questions? And we got to live with it. Any questions? So as an example, here is one which we built on some data where we had men and women have height. You know, we had maybe about 300 men and 300. No, I guess we had about 300 men and 300 women or something like this. Wait, no. What did I say? Yeah, about 300 men and 300 women, something like that, right? And each dot represents a person in height, weight, space. Does everybody see that? And blue represents men, and red represents females, right? And what is the classifier that it found when we did logistic regression? This was the line that was found to separate men and women in height and weight space. Is it a perfect separator? No. On this one in the red region, we had 229 women and 63 men. Okay? In the blue region, we had 223 men and 65 women. Okay? Is it a perfect separator? No. Is it about as good as you can do with, you know, you can see here's a woman who looks, you know, is in the middle of a bunch of men. Here's a man in the middle of a bunch of women, right? You couldn't find the perfect separator, right? But the shape of the curve seems to make sense, doesn't it? And, you know, now with this thing, you give me any height and weight, I can figure out whether I'm going to call this person a man or a woman, okay? And it's going to, and in doing this, if you were close to the boundary, it's going to come back with a probability of being a man or a woman, of being fairly close to a half. If you're far from the boundary, it's going to be much more confident with it. And it's going to be chagrined when you told it that this point was a woman, or that, I guess this point was a man. Okay? Any questions? Okay, any questions about how logistic regression works? So, yeah.
For all the points, we first use logistic regression. Sorry, linear regression to calculate double, right?
No. What we're going to do is, we're not going to use linear regression at all. We're going to say that if you have a classification problem, encoded as a problem where you have a positive net class and a negative class, come up with the following, take your example and come up with this error function. This is summing up over all your training examples, right?
How do we get W in it?
Well, W is, what is f of x? Remember, f of x was the logistic thing. If we go back another slide or two, what was f of x? F was this thing, which is a logistic function with this as the exponent. This exponent was a linear sum of this, right? So what are we going to do as our error function? We're going to take this formula, write it in here in place of the h.
How do we get that Wi?
Right now they're just variables. Wi are if we're trying to, remember, we're going to try to solve linear, this gradient descent thing is trying to solve what is the optimal parameters in parameter space, right?
Okay.
The input to that problem is going to be parameters, okay? The training instances are encoded in this error function. So recognize that we can take your training examples, and there's going to be n of them, right? And we can, by replacing f of x by the logistic function, and by replacing that h sub x by the linear combination of x and y, this thing is a function that is computed from your training examples. And once you have that, it's a function from your training examples, that's a function of w. See, j is a function of w.
Okay, so we'll have many possible
Many possible sets of coefficients, We're going to start from a random set of coefficients,
Okay.
and then because this thing is convex, we're going to move from that to another set of coefficients and keep moving until we look around us and we're at the bottom of the bowl. And then this has to be the best coefficients. And that's going to define what the best function f of x is. Any questions? So logistic regression is a better way to do this binary classification. It is sort of the quote-unquote right way to do, right is too strong a term, but it is, a perfectly respectable way to try to find a separator between two classes. Any questions? Okay, good. Now, what other issues, any questions about that? Yes?
So eventually we are finding the linear combination, right? That is what that function was. Like the
You're trying to find the coefficients.
Right.
Once you have the coefficients, now then, what I'm really going to be doing is saying that on any particular example, my function is now going to be on a particular x vector, right? This is going to be 1 over 1 plus e to the minus w0 plus w1 x1 plus w2 x2, right? Once I know what w is, this is now a function that given any x vector will come back with a score that is going to map to a probability. That's going to be this is going to come back with a probability that x value is in a positive, is a representative of the positive class, right? Okay. So once we have the coefficient things, everything is given, and we use our our gradient descent search to find what those coefficients are, to minimize the training error on all the points we have. Any questions about that? I consider that now, that's now clear in my head at least. Any questions? Okay, good. Okay, so what other issues arise in classification? And there's a bunch of different issues. Let me go through what I can before we run out of class time. One problem that is important in classification problems is that sometimes we consider what happens if, let's say, we wanted to try to find the best separating line between men and women in height and weight space, and we had a large number of men and 1 woman. Okay, does everybody see that? What separator would score best to separate the men from the women in this case? What? A circle, but let's say it's a linear separator. What separator would I do for this one? Okay. Anyone? No. My quest claim is that this looks like a good one, and this one looks even better. Right? And why is that? Because remember, it's saying that all these guys are really, really positive. Does everybody kind of get that? It's got so many things that are very positive. Okay? In this case, it's not even, the fact that there is one negative example and so many positive examples, okay, it's going to work to be far away from it. When you have unbalanced classes, it's not going to be trying to say, oh, how do I do the members of the minority class as well as possible? It gets more points for getting the members of the positive, of the bigger class right. Does everybody see that? So when you have a small number of positive examples and a large number of negative examples, the kind of separator that you get here is not going to be doing what you want. Even I think if we put this, if we put this guy here, let's say that the woman was out here, what would be a better separator? Is it this one? Or might it still be this one here? Okay, where we classify everybody as negative, and you get more points for, yeah.
So the problem here, right, that there just is no good classifier, right? It's not that.
No, the problem here is that because we are weighing each point equally, if one person is, if one class is represented by a few number of people, it is not being regarded. Does everybody see that? Think about an election. You have an election. Okay, if everybody is being weighed equally, if you want to make the majority of people happy, how do you do it? Do you try to govern in the middle? Or do you drive to one end to maximize the happiness of the 51%? Okay? That would be the kind of an argument problem that's happening here. So the point is the rights of a minority are not well preserved, okay, in these kind of classifiers. Does everybody get that idea? Okay? And so this is an argument that we would like to use, should use the same number of positive and negative examples in training a classifier. Okay? Any questions?
So by taking that line, the classifier is getting more points for classifying them?
In this case, by taking one that's far away, it's saying this is such a good classifier that the probability of any of these guys being negative is almost zero, right? I mean, it should be clear that it's more caring about making all the majority class happy rather than getting the identity of the minority class right. That's what should be clear. Okay? Any questions about that? Yeah.
So the problem over here is like we don't have enough number of points of the second class. If we had like many points of the second class as well at the same location, it would be able to get that classifier line.
If we had an equal number of positive and negative, what would we do if we had an equal number of positive and negative things here? If we put the line out here, the positive elements will be very happy, the negative elements will all be very unhappy, and the total happiness is near zero, right? So it's probably going to wiggle around here to try to get something other than zero happiness. Okay? Any questions? So why don't we, so we would like as many positive examples as negative examples. Why is that not always possible? Okay? So the moral should be you should have the same number of positive examples as negative examples. The problem is that often your data is such that you don't have as many representatives of it, right? And if you want to try to identify terrorists from non-terrorists, it's easy to find non-terrorists. It's hard to find terrorists, right? So you're going to have a lot more examples of one class than another. And in many classification problems, that is usually the case. Does everybody kind of get it? There's no inherent reason why the number of spam messages should equal the same number as the number of non-spam messages. Okay? Any questions? Okay.
So if you artificially limit the number of, so like let's say you have a rare versus not rare event, right? And then you artificially limit the number of not rare events, then you're not getting representative, you're not taking a representative sample of the not rare events.
Okay. So let's think what we can do with it. One idea that you just hit on is one way to do it would be I could delete elements from my bigger class. Okay? If I have 1 million non-terrorists and 5,000 terrorists, maybe I'm better off in training my classifier to pick 5,000 random non-terrorists and have an equal number of terrorists and non-terrorists, and then it'll try to find a better classifier. On the other hand, you're saying, but wait, you're throwing out all that information from those almost 1 million non-terrorists, right? And so that's a tension that you would have. But if you have enough examples from the smaller class, you will get a better classifier by throwing out too many elements from the bigger class, right? That much I think we should be convinced of. One possibility is we work harder to find members of the minority class, right? We call our friends, do you have any terrorists that you know? We do something to try to find harder ones. That would be the best thing ideally, but maybe you can't do it. Another possibility is you discard elements from the bigger class, which could work if you have enough elements from the smaller class that there's something interesting to learn. Another idea that you might try to do is, what if we add a weighing factor? We're getting the non-terrorist right. The terrorist right gives us 1,000 times as many points as getting the non-terrorist, as I successfully identifying the non-terrorist. Does everybody kind of picture that? That if we might want to try to add a weight to weigh the minority class elements more heavily, and then say, then solve it. Okay? And this would, in principle, seem like a potentially good idea. But if your minority class is really small enough, that's going to tempt it to overfitting, right? Let's say you wanted to try to predict people who were going to be elected president from people who were not going to be elected president, right? We have a million of people who were not elected president this time. We have one person who was, right? Let's say we get 1 million points for pricking that. What is our classifier going to look like? If hair is hair orange, is dollars in the bank account $1 billion, right? Okay? And you would overfit that. Does everybody see that that's the danger that you would have? Okay? So you got to watch out of that. So one technique that sometimes works, that is it seems like a strange idea, but is another way to beef up smaller classes, is to do random perturbations. Instead of saying, I'm going to include 1 million copies of the positive point, okay, or weigh that 1 million times more, what if I take the input vector for the positive point and randomly add some noise to the values? Okay? And, if I keep doing that, the claim would be that I could create a lot of other examples. It's harder for me to overtrain to fit all of these new artificial examples, and maybe I'm going to be able to get something there. Any questions? But this is a hard thing, but you should realize you are in trouble if you are working with unbalanced classes. And you should expect to have to deal with something to deal with that.
What would be the ideal weighing technique for minority class that does not overfit?
What would be an ideal weighting technique? Again, off the top of my head, in principle, you want the weights of the minority class to totally equal the weights of the positive class. That would seem like the kind of criteria you probably want. But if you have too few real class members of the minority example, it's easy to overfit them because you get a lot of points for getting that one thing right. Okay, so that's the dilemma that we are in. Yeah?
Because how do I ever tell whether my classes are balanced or not? And in the sense, like, in that case, what if the threshold is to the right and it's actually repetitive?
No, the question of whether it's balanced or not, it depends upon my training example. On this particular example, I had 2 things that were positive and 2 that were negative. Therefore, this was balanced, right? If my input examples were, I had 1 million things that were from class negative and 2 things that were from class positive. If this was my training example, I can see I've got trouble, right? I only have 2 members of this class. I've got a lot of members of that class. So whether the class is balanced or not is something I know at training time, right? This shouldn't be, I did this by counting how many members there are of each of the classes I've seen.
But in trying to balance these classes, do you not lose to representation of your population?
There start to become questions here. It should be clear that if it is not balanced, I have problems. Okay? In an ideal world, the 2 classes I'm trying to distinguish, I have equal number of examples from. That much should be clear. It should be clear that if it's not balanced, it's going to be harder for me to do something. And if I don't do something in the right way, I can end up with a trivially dumb solution. Okay? That's what the question is. Any questions?
Assigning equal weights to both the class will classify the problem right. Like that problem, if we assign equal weight to the negative.
If I have equal weight somehow here, then you're right. Then if it's really going to be equal weight, then I would be happy to I have to make this point as happy as I make all the other points, right?
Yeah.
So that is going to encourage me to find something in between there, right? Any questions? Okay, so class size should seem like an important thing. Okay, tell you what. For we're closer. Any other questions about this? Okay, let's say I'll resume with classification, multi-class classification next class. Okay, any other questions about this? Okay, so just as far as stories go, I guess a week from today is when you are supposed to have project progress for proposals, right? What do I want to see? I want to see progress, okay? How do I see progress? Well, one thing is you turn in the old proposal and you turn in the new thing, right? And so the difference between them is progress. Does everybody see that? What I want to see is, I want to see evidence that you are working with this and getting, and learning something. So a good progress proposal report would be, we took the data set, we built this baseline model, and we see that this is a lousy model, okay? And we have these ideas for how we're going to make it better. A bad progress report is one that says, we have developed this very, very complicated model. It's going to include all these things. We haven't implemented yet. We don't yet know how good it is. That is not progress. That's vaporware. Does everybody get the distinction here? Okay? So I want to see some evidence that you guys are working on your data. You are making some form of concrete model, probability, prediction, something or other, and you're assessing it so you have some sense as to how you're doing. Any questions about what I want to see?
Can you submit a Python notebook as a thing?
A Python notebook is fine to submit, but I think I want to see a printout of what you're doing, okay? And you want to show me enough evidence that I believe that this is real and not vaporware. Any questions about that? Okay, good luck, take care, I'll see you guys next week.